Hi, I'm Joel Chen, presenting affordance grounding from demonstration video to target image. This work is done by collaboration with DB, Kevin, and Prof. Mike. Imagine in the future, the robot or AR glass can automatically learn from the demonstration web video to help their egocentric view. That would be so great. Our work pushes a step on this goal. We focus on hand interaction region, also called affordance, grounding from demonstration video to target image. We propose self-supervised affordance pre-training on videos and fine-grained affordance heat map decoding. Our work achieves state-of-the-art on OPRA application hotspot and assist queue benchmarks. Please find our code and demo in this GitHub link. That's all for the quick review of our work. And then let's go deeper. So what we want to solve is a video to image affordance grounding task. Given demonstration video and the target image, we want to predict the affordance heat map on the target image and predict the action. This task presents two challenges. First, it requires fine-grained affordance grounding to distinguish small affordance regions. However, previous methods such as demo to Victor overlook fine-grained details by only deconvolution from 8 times 8 upsample to a 256 times 256 resolution, resulting in significant loss of spatial information. Another notable approach, interaction hotspots, is based on gradient cam to limit it to a 28 times 28 resolution, which doesn't support fine-grained affordance grounding. The second challenge is limited data. All public datasets contain less than 20,000 video to image pairs in total, which may negatively impact the grounding performance. Our work proposes a new method, affordance transformer, namely Afformer, to address the fine-grained affordance grounding problem by multi-scale cross-attention for fine-grained heat map decoding. And we also propose a mask affordance pre-training method, namely mask ahead for limited data problem by data synthesis and pre-training on the generated data. First, let's dive into Afformer. With the video and the image as inputs, we use a shared encoder such as ResNet FPN or VIT-DATE to encode both image and video features. The image feature is encoded as a special feature parameter prepared by a course to fine decoding, while the video feature is encoded as a temporal parameter at a fixed high resolution. There are two reasons. First is to maintain the spatial high resolution to clearly see where the hand interacted, and reducing in temporal to reduce memory cost. Then we start to decode the heat map. We regard the image feature as a query and the video as a key, using a transformer decoder with self and cross attention layer as a core module to decode. This is something like for every spatial location in the given image, we determine it by watching the video spatial temporal locations to decide if it has been interacted. We can arrange layers in a hierarchy from low to high resolution. The final course decoding feature is upsampled and combined with the current level query, which is then input to a transformer decoder block with the aim of refining the previous course result at this level. In this process, we use a triple stack of layers, followed by a deconvolution layer to produce heat map that matches the target image size. The action output uses a average polling and an MLP. The heat map training employs KL divergence loss, while the action loss uses cross entropy loss. So our Afformer significantly outperforms previous model. It achieves larger than 30% better KLD compared to previous SOTA and fine-grained on a fine-grained OPRA dataset. Furthermore, it also performs well on the coarse-grained OPRA, like 28 times 28 resolution and the EPIC hotspot dataset, and it builds a new SOTA on this dataset. We have presented a Afformer and fine-grained affordance grounding. Remember, we still have a challenge of the limited data. Our idea, mask ahead, is using online demonstration video to synthesize training data samples so that the network can learn from this data to improve the grounding ability. The first step of mask hand is to train a strong hand interaction detector. Human hand and the interaction state is easy to detect due to their clear pattern. We easily trained a precise model on the 100-day of hand dataset. And then we should convert the affordance grounding to the hand grounding task. This is original video to image affordance grounding task, and it leads to predict the affordance on the target image. But in the converted task, it changed to predict the imaging handbox to operate the same region in the video. Since the affordance region is near the hand, so this task shares the similar ability with the video to image affordance grounding, and more importantly, we can use the trained hand detector to generate data. Let's begin data synthesis. First, we use our trained hand interaction detector to sample a clip of 32 frames containing at least one frame of the hand interaction. We use the highest threshold, such as 0.99, to suppress the false positives. Inspired by SuperPoint, which is a well-known self-supervised image matching study that generates another view by itself. And we can also generate the target image by the video clip itself. Here's our process. First, we select the frame containing interaction and mask the hand box with a larger and random pixel mask. So this is to make the model predict the precise hand location and to improve the fine-grained grounding ability. Then we randomly add another mask with same size. This is to avoid the easy solution of predicting the mask. After that, we also add a perspective transformation to simulate the perspective change. Finally, we can train the former using the generated data. We can know the ground truth map since the map comes from the transformed hand box. There are some mask hand generated examples. In our experiments, mask hand actually helps affordance grounding. First, mask hand zero shot approaches surpass previous fully supervised method. And second, the mask hand patterning further improves the performance. Assist the Q benchmark when the dataset is very small. Mask hand significantly improves the performance. You can see that the zero shot prediction is very close to the ground truth annotation. Application of our method is on AR glass. It can learn from the instructional video and then plot the region which user should interact. That's all for my presentation. Thank you for your listening.